All right, well, why don't we get started? I'm sure the room will fill up even more as more people arrive. So, welcome everyone. Glad to see everybody's here. Welcome to the May virtual monthly meeting of the astronomy section, Rochester Academy of Science. In case you don't know me, my name is Mark Minerich. I am the president, and glad to see so many faces and a bunch of people in the room. I'm going to mute this. There we go. All right. You can unmute yourself. I've muted you, but you can unmute yourself if you need to speak. So let me get started. So first, I want to thank Dave Pesch again and his company Expudo.com for donating this service. And Dave has explained he's upgraded his server. We can actually have all this video on, hopefully, while we do our presentations this evening, so we can watch each other's living rooms, bedrooms, offices, whatever in the background. Cats wandering across keyboards. Thanks to yes. So thank you, David. Thank you very much for this service. All right, so how this is going to work, I just muted everybody. If you want to speak, you can. You can unmute yourself. You can also use the chat up on the top is a public chat. If you expand that over, you can type a message publicly, or you can send it directly to me or anyone in particular if you want to speak to what's going on. And I would advise that if you once Richard, I see Richard's here, our main speaker. If you want to ask questions of Richard during his presentations, let me know, or you can put it in the public chat or send me a chat directly, and then I'll get that over to Richard during his call or during his presentation to answer those things. If it needs to be answered right away, or if it's something we can queue up for the end of the presentation, and then I'll unmute everybody at the end of it. So Richard says, I will co-host you, Richard, once I get the presentation there. So if you want to, we'll get you uploaded right at the end of my presentation. So if you have a headset, that's the best way to use this if you have a headset. If not, don't worry, not a big deal. That way you don't get a lot of feedback of what's happening, but for future reference. All right. So welcome, everyone. This is our agenda. I'll do a welcome. We'll have some announcements, and then our feature talk by Richard O'Shaughnessy, a theoretical gravitational wave astrophysicist at RIT. He's spoken with us a couple of times on gravitational waves. It is a rapidly developing field. So I put part 3 because in the last couple of years, he's been here, and there's more and more happening in the field right now with LISA coming online and all the LIGO information that's out there. I'm sure he's like a one-armed paper hanger right now. So we'll see what's happening in the field of gravitational waves with his talk to end up our evening. So let's get started. Anybody able to do some observing recently? I'm going to unmute everybody. So if you've done any observing, been able to see anything, let us know what you've seen. I know I saw beautiful Moon and Venus dancing around each other the last few nights, or a couple of weeks anyway. Anybody else see anything?
Yeah, I saw Venus myself.
Yeah, Venus was beautiful. It's very, very bright with the moon at night.
Yeah.
Moon's moving a little further and further away from it each night.
Yep.
All right, well, moving on, it's time to renew your membership if you haven't renewed it. There's a way to do that. I'll show you that on the next page. You can do that electronically. You don't have to contact Bill directly or in person. I'll show you how to do that through PayPal if you have PayPal. And on the same note, if you have a key to the Ferris Center, now's the time to renew your key as well. We'll let Bob know that you want to renew your key. And you could do that through PayPal as well. I know Bob's going to have something happening I'll show later in tonight's presentation, what's happening on there at the site. So to renew via PayPal, again, I will have this presentation uploaded onto our website by the weekend. So I'll get that to you, Peter, to upload. But you can use this page to renew via PayPal. Go to the PayPal site, and there's our email address to renew, ASRASPayPal@gmail.com, and you use that as your PayPal payment form, And if you send a note to that site, you can also give attention to Bill with what level you're joining up with. Or if you want to pay your key that way, you could do that as well. Just let us know what you're doing if you use PayPal to do that. All right, recent events. How many of you were able to see the National Space Network's webinar last Thursday of the lunar landing sites? How many were able to see that? Many? I thought that was pretty interesting. Anybody want to comment on it? What'd you think, Val?
I thought it was really cool, and I didn't know that the simulations that he was using existed. So NASA's got this cool program where you can go and basically zoom into the moon and see all of the highly detailed images of the surface. So I thought it was great. It was a really great summary of everything we've done in the past and where we hope to go in the future. Worth watching.
Fascinating webinar, I thought. And that's recorded, so you can go back and watch it again. The image that I'm showing here is an image where that image is showing an anomaly on the moon, but really that's just all surface dust from a magnetic anomaly on the moon. That was one of the more interesting things that I saw in the whole thing. But there are some fascinating things, areas of the moon that we've yet to explore. So there's a lot more there that we could explore. And this link will be on this. I'll load this up as a PDF, so you can pull the link right off of here if you want to visit it again. If I go to the next page, there
oh, sorry.
I'm sorry. Go ahead, Marty.
Are those based on lunar reconnaissance orbiter photos?
Yes.
Yeah, because that's what I used for the MEAS stuff for the for the lunar module. I mean lunar stuff.
If you listen to the webinar, he tells you where to go. NASA has a whole simulator you can go to. You can actually fly over the surface of the moon. And queue up all these different places to go to. It's a pretty cool simulation you can use. And so on this next slide, I have a whole list of, I wanted to see what other recorded webinars they had, because they did record this one. And here's a handful that I found that look really interesting. I actually watched the Voyager spacecraft one, but there's a whole bunch of them on there. I would encourage you to go to the Night Sky Network YouTube page, and you can look for any of these videos. They're all about an hour long. They're not ridiculously long, but if you have an hour to burn, like who doesn't have an hour to burn right now? There's some really interesting stuff at the NASA Night Sky Network as far as the recorded webinars. So highly recommend that. And again, this will be available on our website later on if you want to further reference it. Was anybody able to visit the NEAF virtual experience? I didn't get much of it, so I don't know if anybody else did.
I got a little bit of it.
What did you see, Marty?
I poked in on the original. It was more the displays, the product displays.
They did have the product displays up.
Well, they did for just that one day. I don't know why they didn't leave them up. I would have thought they would have.
Huh, interesting.
I mean, it's kind of like free advertisement if you think about it.
Yeah, absolutely.
So I was surprised at least they didn't leave them up. I expected them to.
Well, it sounds like they're going to have an actual NEAF again this fall. So
maybe in the fall, right?
Yeah, it's an interesting thing to go to. I don't know that I wouldn't go every year. That's just me personally, because there's a lot of cool things to see there, and you get the latest in equipment, and you get to see, touch, and feel some really great equipment if you're interested in that stuff.
Yeah, but it is a trip. It's a haul.
It is. It's in Suffern, New York. It's a good 6-7 hour drive. So
yeah,
it's a haul. Yeah. Anybody else comments on NEAF? All right, coming up this weekend. I don't know. Is Bob McGovern on? He is. Can you do you have your voice activated, Bob? Bob's frantically trying to get his voice going, so I'll talk for him. But Bob is looking to have some people gather tomorrow to help clear that gravel sidewalk, which is weed infested right now. Our plan this year is to pave that with a couple inches of asphalt because of keep out the weeds. And so we need to, in order to pave it over, we got to get all the weeds out one more time. And so we're having a weeding party tomorrow to try to get one last shot at getting out the weeds. And there are a few things to do. We haven't had much activity at the Ferris Center. So we do need to clean the buildings. And this stuff doesn't need to be done tomorrow, but it can be done at any time. And if you can help out with that, let Bob know that you can help out. You could do it on your own. A lot of this is pretty solitary stuff as far as vacuuming the buildings. We want to paint and caulk some of the wood trim in the doorways. I know that some of the trim in a couple of buildings needs to be done. Let Bob know if you can lend a hand with that, and you don't have to do it any one particular day. So that's stuff going on at the Ferris Center. Again, if you want to observe at the Ferris Center, I put this in my notes at for the newsletter. Feel free to use the Ferris Center on your own. I know that we're under travel restrictions or whatever, but certainly observing is a pretty solitary thing as long as you're using your own equipment and your own eyepieces. We don't want to risk any contamination with the club's eyepieces, so I would ask that you just use your eyepieces if you're using a telescope. Any questions on that? All right. Another streamed event. This is happening tomorrow night. The Lowell Observatory down in Arizona is having a National Astronomy Day. So there'll actually be a streaming they're observing out there in Arizona at 6 p.m. Pacific, which is 9 p.m. our time. There's a YouTube link for it. You can look that up online. Again, this will also be available probably by tomorrow night anyway. If you can get that up by then, Peter, appreciate that. They'll be streaming observing at the Lowell Observatory out in Arizona. You want to see some dark skies? That's some dark skies over there. And then thanks to Nick Lamidola, Nick sent me a note today about Comet Swan. He pulled up a little thing in Stellarium. He actually added it to his list in Stellarium. And there's a picture from spaceweather.com from yesterday of Comet Swan. Now that Atlas has broken up into little pieces, this is the next star in our neighborhood as far as comets go. And on the next page, and I will send you all a PDF of this, so it'll be in black and white if you want to use it. This is where Comet Swan will be in mid-May, from about the 14th at the bottom right to the 22nd at the top left. And it cuts through Perseus, which at this time of year means it's pretty early in the morning. So at about 3:30 in the morning till about dawn is when your best shot is at looking or seeing Comet Swan. And if you look on the left in there, I put in the brightness magnitudes for those dates every couple of days. It's gonna be at its brightest right in the middle of that what is it, 8-day period. And it's really not that bright at 5.8, but it's really bright enough to see with binoculars or certainly with a telescope. But that's where it will be. I will email the email list with a PDF chart of this. It'll be reversed, so it'll be white background with black stars, but you'll still have that dotted line with the dates on them for when Comet Swan. If you're interested in trying to find the Comet Swan, the current star at our skies, or current comet in our skies. Any comet hunters out there? Are we going to look for this comet? Nick's going to look for it, right, Nick? He's muted. All right, upcoming events. So our next event will have or hopefully we can, for June, we can actually meet. We would actually be meeting at the Ferris Center tonight if it wasn't for the situation we're in. But we will try to meet in June at the Ferris Center. We'll see where that goes with with our governor and what will be happening here. And David Bishop will be giving his astronomy year in review, and always a very popular talk because it changes from year to year for what's happening in astronomy. Dave, you want to say anything about what you've got on cue?
Well, I've got a few new slides. Can you hear me?
Yes.
I've got a number of new slides. I'm just putting together the show. I'm actually going to be doing it for the Syracuse Club next Friday night. We have some interesting extraterrestrial helicopters, 2 of them, that are in the show, that are being launched by NASA. So that's part of it. And some really strange things happening on Earth and in space. Things that have never happened before happened last year. And of course, I'll be covering those as well.
Sounds good. Sounds good. Okay. I am going to now, hang on, I gotta. All right, so I'm promoting Richard to our presenter. Richard, are you there? Hang on. I think that's it.
Yeah,
Any other? All right, you there? You hear Richard? All right, I'm going to promote you to presenter. Let me introduce you first. So let me introduce Richard O'Shaughnessy, professor at RIT, and he's going to load up his presentation on. Let me put you back there. All right.
How do I want it? I uploaded the presentation already. There we go.
There you go. Now we see it. And wherever
All
you
right.
move your mouse, we get a nice little red dot, so you can point out
Okay,
your stuff.
I wonder if this can work. Let me see if this will work. Aha. Okay. So this is the background movie. So it's been a nice year in gravitational wave astronomy. There have been a lot of really cool things going on. Unfortunately, I'm working on them, and I regret that life has intruded, and we can't tell you about all of the incredibly cool things that we wish we could tell you about, of which this is one, which I can't. But there have been way too many new discoveries of things we definitely haven't seen before that are transforming our view of the universe. And this is one of them that I'm going to talk about today. And here you can see the in-spiral of 2 black holes of a very different size that I'll be talking about in a bit, emitting gravitational radiation, which is shown in realistic form on the bottom. As they get closer and closer and they spiral around each other, they're sending energy off to infinity, getting closer together, moving it faster and faster and faster, until finally they're going to come together in a moment and merge. And you're going to see the 2 horizons. Well, one of them is being distorted by the other through a tidal distortion. Then they merge, and then they settle down to a single black hole. So that's one of the types of neat things that we've been finding. There are other types of things. There are things where we don't know exactly what it was that we'll talk more about in a bit. But that's where we are. Let me turn this off and go back to stop sharing your video. There we go. All right, so this is an update. It's going to get a lot cooler in about a month or so. Hopefully less than a month. I can't share my other screen, but if I could, you would get very excited because there are a handful of us who have to do all this stuff, and it's a hectic time, but it's exciting. So what can I tell you? So the beginning of this talk and the end of the talk, because I wasn't allowed to put in all the cool stuff in the middle, are somewhat similar to the report last year. So we're just going to give you a taste of stuff that I wish I could show you real examples of, but I'm just going to try to give you a hint of what is about to happen. All right, so where are we? So what are gravitational waves? So gravitational waves are this is the background, a new window of the universe. If you've seen this talk before, this is the same background at the beginning. Just like light is produced by accelerating charges, here I'm going to make my charge accelerate. There it goes, back and forth and back and forth. What it will do is it'll emit radiation moving outward that we can see. Basically, causality enforcing that we're only learning about the motion of the charge after a delay. Now, there are two signs of charge, so therefore our positive charges and negative charges come together. This screening limits the net effect of charge, and therefore you can't produce as easily enormous electromagnetic waves. They tend to cancel out, which is good because electromagnetic interactions are very, very strong. They're very easy to make and detect, but they're easy to obscure. Usually I put my hand in front of the screen at this point to block out the waves, but you can put your own hand in front of your own screen as a visual aid if you so desire. Now, gravitational waves are different in that they can be produced by any accelerating mass, so that's the same. They're also transverse waves. They have they're spin 2 instead of spin 1 for those of you who care about these things. So they cause us kind of a transverse stretching and squeezing an elliptical shape instead of a vertical motion up and down, which I'll come to in a second. This is a very weak interaction, which is critical. You're not a pancake, which is important for you, not being a pancake, but that means they're much weaker than electromagnetic interactions, so therefore they're very, very hard to make. However, once you make them, they're very, very hard to obscure, which is the essential feature that allows us to do gravitational wave astronomy. It allows us to reach inside these most energetic events in the universe. So there is supposed to be a video here, and is that going to work? Let me share my screen. Well, I will do it diagrammatically with my little icon here, and then we'll just move on. What a gravitational wave detector does is basically it's 2 meter sticks, and you're looking at the relative change in length of 2 meter sticks, one this way and one this way. And you want to say, are there changes in the relative length between these 2 meter sticks? Relative length changes being easier to measure by using interference. So the idea is you have light going down one arm of your interferometer and light going down the other arm of your interferometer. And this direction, normally there'll be no light if they're perfectly matched. But due to small changes in length this way and this way, you'll get some cancellation and light will come out in this direction. So we've found these things. I think you may have heard. So on the top panel, and the resolution doesn't appear too great, at least on this screen. On the top panel, you'll see the actual gravitational wave signal. This is filtered a bit. We have a lot of noise at low frequency. That was filtered out, and a couple of spectral lines were removed. But this is pretty close to raw data. On the bottom panel, it's kind of a time frequency, kind of a spectrogram. You can see a representation of that top panel. On the right, we've superimposed the signal in a different detector. We've kind of time shifted them to account for the time of flight across the Earth, and then flipped them inside because the detectors are flipped, kind of reversed from one to the other, and they agree very well. There's no processing aside from the filtering in that top panel, so we definitely detected something. More important, and I want to draw your attention to the error bars on the bottom plot. So what we do is we can say we know it's a gravitational wave and not a pigeon sitting on top of our beam tube, or a crow, trying to dig a hole in it, because we can compare it systematically to a lot of template waveforms, so patterns that we know to be a representation of these merging black holes that we saw, ideally from these detailed supercomputer simulations, which is that line shown in red. We pass it through a model of our detector, like a model of our ear, for example, and we get this thin red line. This is not a arbitrary fit to the data. This is an actual supercomputer simulation, just like the one I just showed you, that was chosen to try to fit this data, and it does a great job. The solid contours that you can probably see just barely is a continuous model that tries to interpolate between these the kind of things that you get from the red line. And the gray band is a non-parametric reconstruction that tries to fit self-consistently the signal that's seen in the two detectors. So the gray band is completely non-parametric. It has no knowledge of general relativity at all. And they're all giving a very consistent answer that we see the signal. And so these are the sorts of tools that you'll see applied in things that you will hear about more soon that are exciting. So it's great we find these things, and the process that I just described of taking this data and then comparing it to a library of simulations that we have, we just keep trying and trying and trying. The ones that fit better, we say are more likely. The ones that fit terribly, we say are unlikely. And this allows us to construct a inference to infer the parameters of the black holes that are responsible for the signal. So we can figure out what the masses are and some other properties that I'll talk about in a second. This is a movie. I already showed a movie, and I just realized that this is not going to render this way, so I'm not going to do that. I will go back and show the other movie again. So we just finished the 03 observing run, and unfortunately, I had to truncate a little tiny bit early, as you can see here. But it went pretty well. In 01, we had a couple of events, 2 confident events and 1 kind of middling thing. In 02, we had a dry stretch for a while, then things started to get really exciting near the end because we made some adjustments to make things a little bit more operational. And you'll notice that in 03, and we've gotten rid of the times when we weren't on, because that was more depressing. So when we're on, suddenly at the end of 02 and now into 03, we starting to detect these emerging objects at a much more rapid pace because our detectors are somewhat more sensitive, and our event rate goes roughly as the cube of our measure of sensitivity. I should point out that the detector is going to get even more sensitive in the near future, so the steepness of this expected growth in 04 will be frighteningly large for those of us who have to deal with a deluge. So it's a very exciting time to deal with this sort of data. We have quantity is a quality all its own. When you have this many events, there's things that you never saw before, because when you only had a handful, you're not going to find the slightly uncommon things. Superstar baseball or basketball players are not going to show up in your average little league team. But when you have a lot of them, suddenly you start to find really unusual and exceptional things. And sometimes those unusual and exceptional things challenge the story that you deduced from the previous things. And so we're beginning to see quite a bit of that now. And that's what I'm going to try to focus on as much as I'm allowed to in the slides to come. So lots more stuff, in short. Some of it not like what we saw before or anyone's seen before, and we're still digesting. So good times. So what can we measure with gravitational waves from a binary black hole or a merger? So we can tell basically what the two things are. Insofar as they have black holes have mass, and they have spin. That's all they have. That's the no-hair theorem. Basically says black holes are endowed with mass and spin and nothing else. And charge if you want to be pedantic. But that's 0. Now, we can also detect mergers of anything else. So if you had a jelly donut around a black hole, in principle, it emits gravitational waves. And in principle, you could detect that jelly donut if it was, well, a really massive jelly donut. The problem is a jelly donut will typically be ripped apart into small shreds before it gets too close to the black hole. And just how rapidly it gets ripped apart, if it wasn't a jelly donut, but say a neutron star, when it gets ripped apart tells us about how strong the constitutive forces are that hold that jelly donut or neutron star together. So we can measure not only the mass, what I'm illustrating here, but also the properties of whatever material is holding objects together as they approach black holes. Black holes, in effect, those mergers act like cosmic accelerators, and we're getting to look at the process of them being torn apart with a movie that's being provided to us by the universe. So it's great. But let's look at the mass, for example. So this is the mass of the first how many am I? 10-ish detections. It doesn't have the binary neutron star, which is down here, 0817. But it has a whole bunch of objects. Now, you might be looking at this, and we'll come back to this, why things are where they are. But you know that most of them look like they're equal mass. I'll come back to that in a second. There's a lot of degeneracy in the way that these error ellipsoids are extended in this way. That's because the waveform is very sensitive basically to the overall mass scale, which goes in this direction, and not very sensitive to the mass ratio, which goes in this direction. So one of the things that we saw that we thought was cool recently is an oddball binary neutron star, whose I can give you its name. It's 190425 Z for those of you who are keeping track at home. So we've seen a neutron star emerge before, and it was really cool. It got torn apart, it emitted light. It was fantastic. We saw another one, and there was no light that we could find, that anyone found, so we were sad. However, we knew a secret that no one else knew. We knew that this neutron star was really, really exceptionally heavy compared to all the other neutron stars we see. Now, there's not much else that we know about this signal because it's pretty heavy and relatively far away. So it's not as cool as the first neutron star, which was more a typical, like the neutron stars we see in our own galaxy. This is the total mass, and this is basically a histogram of how often these things occur based on our observations of our galaxy. So there's a lot of pairs of neutron stars in our own galaxy that you see with radio telescopes, for example, timing them. The famous Hulse-Taylor pulsar. These are all lower mass. Each one is about 1.3-ish solar masses, sometimes a little bit less, sometimes a little bit more, but the binary systems tend to be around here. There are a couple neutron stars that individually are about 2 solar masses, but they typically don't occur with pulsar companions. You tend to, pardon me, find those in accreting white dwarf systems. What we found is a pair of neutron stars that together is very massive. Now, this could be something like a 2 solar mass star plus a 1.3 solar mass neutron star. So there could be a heavy neutron star with a conventional neutron star. It could be 2 mildly unconventional neutron stars. We really can't tell. It's hard to do this. And to illustrate just how hard to do this it is, we show 2 different answers depending on 2 different assumptions. But generally speaking, we're pretty confident this is a heavy neutron star that's unlike what we've seen before. Now, why would you care? Well, the masses of heavy objects give you a clue to how these are all formed in the depths of massive stars. Just how frequently you make things of different mass. So, for example, if all neutron stars that you made in binaries tend to be at low mass, what you might infer is, oh, neutron stars are born at low mass, and the high mass ones maybe they grow by accretion. However, we have these 2 things. They're in a pair. They almost certainly didn't grow by accretion because they couldn't have accreted from each other in most scenarios. So that gives you hints that maybe neutron stars can form at higher mass. Conversely, and I'll get back to this in a bit, what about forming black holes? Does that mean that there's a possibility of forming things that are even more massive and possibly in this region over here where you would have 2 black holes? Is there a continuous mass spectrum that goes between neutron stars and black holes? We previously thought there was a gap because we didn't find anything. Who knows if that will change? Well, I know, but you'll find out soon. All right. The other thing that we've seen, and this is a review from before, is a distribution of the black hole masses. So we didn't find previously any low mass black holes, and we don't have anything that we're talking about yet. Well, that may change, but so previously we have no way of determining if the number of black holes as a function of mass, if there's a lot down here, which is shown in the blue shaded curve, that could be true, or if the distribution drops off. We really don't know. We're limited by the fact that we're not very sensitive to low mass black holes. So if we go back to our diagram here, whoops, I want to illustrate. Our sensitivity increases with mass, and the underlying number of black holes drops off with mass. So at really high mass, we don't expect to see anything. Conversely, as we go to low mass, at really low mass, unless the event rate is really, really high, we don't expect to see anything down here because our sensitivity is too low. Over here, the absence of things is kind of surprising because our sensitivity doesn't go down. So this must mean that there's nothing here, or the event rate is lower out here, and it's lower out here. So that tells us something, and that was the central conclusion of the O2 search, is the event rate goes down at high mass, and there's a preference for equal mass mergers. We also know that less massive black hole mergers are intrinsically more prominent. This thing slopes upward, but that's about all we could say at the time. We will be able to say more now. However, it's a lot easier to say more when you have one really exemplary member of a class that you can be sure and confident is unlike the things that you've seen before. And so this is another example. This is, well, it's about a year ago now, 1904 12M. So 190412M is shown here in a spectrogram form. And looking at that, you might not appreciate how exceptional it is and how helpful it has been to us. And I borrowed some of these slides from Max Easy's talk from the APS. So the key thing about this thing, and this is that movie that I showed at the beginning, is this is an asymmetric merger. One of the black holes is really big, and one of the black holes is tiny. That is not where we saw things before. That's definitely well off anything that we had seen before from the previous survey. And in fact, it's in some ways it's qualitatively different because we're now confident, as we weren't before. There was still some thought that maybe all black holes were equal mass, so there was a strong preference for forming equal mass binaries. It's not entirely sure how that could be done because most people who do these formation models predict some range of mass ratios. So having a completely compressed mass ratio distribution would have been surprising. But no one had found anything yet where we were sure it was an equal mass, and this is one where we can be confident that you have an asymmetric binary. The other thing to note about these this asymmetric binary is one of them is pretty big. A 30 solar mass binary is about as big as we get. They get a little bit more massive in O2. And an 8 is kind of near the bottom end of what we were seeing. So if you go to this distribution back on the previous slide, we're talking about up here with this. So a pair at the extremes of what we thought was possible. So that is that's why it really is so striking from an observational perspective. Additionally, there's some other reasons why we thought it was interesting. In that, if you look at that merger a little bit more carefully, that merger, its radiation pattern, is kind of complicated. Now, so this is a little bit mathy, but if you break it down into its a radiation pattern down into kind of its fundamental tones or overtones, so kind of the fundamental patterns on the sphere. These are the spherical harmonic decomposition. Then what you see is the radiation has some natural angular frequencies that it has, which typically correspond not only to angular frequencies but actual overtones of the gravitational wave signal. And it turns out that in addition to the normal overtone, because it's a quadrupole tone, it's twice the orbital frequency. There is another overtone that was being emitted at 3 times the orbital frequency. And you can see here is the dominant frequency at twice the orbital frequency. And at 3 times the orbital frequency, here is the other offset. So there we go. So having that there allows us to pin down the properties of the black hole more precisely. Because we have more radiation, what you can do is you can, that has a more complicated angular dependence. What you can do is you can pin down, the properties of that black hole more precisely, but you can also tell things about what its orientation is. Now, telling it its orientation is actually really important for other types of binaries that we may or may not talk about in the future, like neutron star binaries, because if you measure their orientation, you can, like a black hole neutron star binary, you can figure out its distance, and using its distance, you can do it all sorts of other things if it were to emit light, which would be neat. So we really, really like the fact that it has these more complicated radiation patterns at these higher order modes. What else is interesting about this? So this black hole, we're pretty confident has spin. Now, there weren't that many other black holes that we had seen where we were confident there was any spin at all. In fact, all those black holes that I showed in 002, only one of them, only one, I'll come back to that in a second, we were confident had spin at all. All the other ones could be consistent with a spin of 0. The black holes were sitting there where they were the most boring possible, which seemed odd because we thought, well, stars generally rotate, and when they collapse, the angular momentum doesn't go away, so the black holes should rotate, and they should rotate pretty darn fast. So it was a little odd to many people that all the spins turned out to be 0. And we'll get back to that in a second. This is the second case where we were pretty confident that the black holes, the pair of black holes has some spin. So this right panel is showing the mass ratio and the spin parameter. That's a kind of a projection of the spin vectors along the angular momentum. And we see that this parameter, it's not very well determined. It depends on exactly how you do the calculation, but it's not 0. So there's some spin. And it's not infinite or not 1. So there's a range of answers. And you can see that we also don't get the mass ratio very reliably. There's a degeneracy in the 2, but we can be confident there's some spin, and we can still be confident the mass ratio is significantly different from 1. Now, why is that interesting? Well, okay, black hole, a pair of black holes have spin. the key thing to remember is the spin of a black hole, its spin vector scales as its mass squared. And that second black hole is pretty tiny. And that means that most of this spin comes from the first black hole. That's important. So if the first black hole is spinning, that says that we're confident that big black holes spin fast. And so why is that surprising? Well, the previous time we saw spin was on a small black hole. And all the other big black holes, and all the other black holes, period, looked like they had no spin. And so someone came along and said, well, I bet that all black holes, in fact, all stars rapidly spin down. This is a real paper. People are very seriously thinking about this for a while. Very seriously saying all black holes spin down. And all stars that make black holes spin down. And so, therefore, the natural spin for a newborn black hole is 0. To very high precision. And the only way that you can get a black hole with spin is if it accretes. Now, that's harder to reconcile with this scenario because it's harder to spin up the black hole. It is possible. The odds do favor the big black hole having spin rather than the small black hole. And it's very easy to make these sorts of binaries do the right thing. So these are not hard to make, but it is hard to reconcile with the idea that natal spins are 0. All right. So what would surprise us? Since this was not that surprising. So now let's go to be a little bit more forward-looking. Since I've exhausted what I'm allowed to tell you, unfortunately, that will change in a couple weeks, but not today. So something that would be surprising if we were to find it would be if one of these black holes were really asymmetric, not just 30 to 8, but really big or really asymmetric. That would be very different than what we've seen before. In fact, if both of them were big, it would be very different than what we've seen before. So something really huge or something really extreme. So is that even possible? So I'm going to tell you a story of one way that you could make these things that I work on. So it's a story that I particularly like. So let's suppose you have a big black hole, supermassive black hole, and then a bunch of gas. And you drop little black holes in this gas, like little, I don't know, gumdrops in a whirlpool. And for various reasons, this is like a protoplanetary disk problem. The bigger gumdrops are going to spiral in more rapidly. They're going to migrate more rapidly. They're going to catch up with the smaller gumdrops and eat them up, and make so you'll get bigger and bigger things moving in, and these tend to naturally create very asymmetric and very big pairs of black holes. Also, these things when they merge, the black hole, for reasons I'll talk about later, the black hole jitters the disk a little bit, and it can also emit light, which is super cool. So there would be an observational counterpart to these that people could look at. So this sort of thing would naturally produce this super extreme thing that we think would be cool to find. More generally, the same sort of process. So this is an example. This isn't the only way that you could make something this extreme. This sort of process would happen if you have a pair of black holes and you merge to form a bigger black hole. If that big black hole stayed around, and it could merge with other black holes. This is a general process, this kind of a coagulation cascade that you would see in a lava lamp or something, or little tiny globules forming to form bigger globules. It's a general process of hierarchical formation. And this is going to happen naturally if you have black holes that are confined into some condensed region, like a globular cluster or a nuclear star cluster. This will produce black holes that grow in mass, and also because you have them spinning right before they come into contact, they retain a little bit of angular momentum, and so they naturally, this final black hole tends to be rotating because the two black holes that come together in a circular orbit. So that final black hole has to be rotating. So black holes grow in mass and also in spin. So this is a great scenario for producing these extreme objects. You get high masses and you get extreme spins that we haven't seen before in observations to date. The problem with this scenario, the classical problem, is that when you make two black holes come together to merge, there's actually not, they don't just form one black hole. That one black hole wants to recoil and be kicked away at a very high speed because they emit gravitational waves asymmetrically, preferentially in one direction, and so they shoot away at a high speed and get ejected from whatever is confining them, unless that confining potential is really strong. So if that confining potential is really strong, it will hold them in, and you can make really, really big, super extreme black holes. So that is one scenario. So how do you tell if this is actually going on? So the classic argument that I and some other people made a long time ago was one way to look for this is the masses that you see. You say, do you see really extreme masses? But there are a couple of different hierarchical formation channels, etc. What you really want to look for is, are you having the spin orientations of your system in a dynamical environment? You expect all the stars to kind of be oriented at random, and so you get in this previous configuration. These black holes would have some random orbital plane, and therefore some random spin direction, which will be different from any particular merger, from merger to merger. So the spins are all scattered around. Whereas if you have a pair of stars that are orbiting around each other, they tend to have tidal interactions and tend to align their spin directions with the orbital plane. And so one would expect, for example, in the second scenario where you have forming stars, what you would expect is the stars spins. You'd start off with a pair of stars that have spin, and one of the stars would blow up and tilt the orbit, and then the other star would be torqued and then blow up. That the spin orientations would still have some tracer of the original angular momentum direction, and therefore you can use the spin orientations to kind of, as being preferentially aligned, as an indicator of this star-like formation, and you can use random spins as a tracer of it coming from a dynamical scenario. And so this dichotomy is something that we are in a regime where, with 50-odd events, if any of them are spinning, and we just said that one of them is, with 0412, if there's spin out there, we ought to be able to tell it apart. So soon, we'll be able to say something. Conversely, if they are preferentially aligned, if the spins are preferentially pointing up, that if they're dynamically formed, we'll know. We'll have some indication of how often that happens. If they're not dynamically formed, we could start to get a measurement of how misaligned those spins are, and then measure how the properties of when stars explode. So that would be cool. Previously, we knew that spins were small, but now we're starting to get evidence that spins are larger, and I'm going to skip these two because that's technical. All right, so to start to wrap up, so what other things can I not talk about, but will be cool? So there's a lot of other things that we can measure with gravitational waves from black holes. I talked about the mass and spin briefly. The mass will find some exciting things soon. The spin, its magnitude, and particularly its misalignment and its trends with mass will allow us to probe different formation scenarios for black holes. The other thing that we can measure is how far black holes are from us, and that's going to basically tell us the star formation rate as a function of distance. I think I had these slides out of order. Yes, there we go. They'll give us a redshift distribution as a function of time, ideally, in the long run. So ideally, what you can do is just say, I've got 5,000 black holes at this distance, 30,000 black holes at this distance, 100 million black holes at this distance, and so forth. You basically bin them up in a histogram, and you measure the star formation rate as a function of redshift. So very easy to do. This is for the future. This isn't what we can do now. But even with what we can do now, you can still, the error bars are a lot larger. This is with, a few million events. But, even with only 40, you can still get a rough idea of the shape of the star formation rate as a function of redshift. So that's cool. The other things that you can do is directly measure the expansion rate of the universe. You've got so many black holes that you can start to pin down statistically if a black hole is associated with different host galaxies, and thereby measure the expansion rate of the universe that way. Not without even necessarily knowing which galaxy any particular merger came from. So no confident host associations, you can still get the expansion rate. So that's another sort of thing that's going to start to be accessible. A lot of us are working on these dynamical formation scenarios, and one of the really interesting things that occurs with dynamical formation is eccentricity. You might or might not hear more about that soon from a number of channels. But people have been very excited about this because this would be another unique probe of the last time that a black hole was interacted with something dynamically. Because gravitational waves emit radiation, they tend to circularize their orbits, and so any eccentricity that's left over is really an indicator of something really exciting just happened right before the binary merged. There's also some other things that you could in principle measure, but that's harder. And I think I'm wrapping up now. So to conclude, we're now reaching the point, and I really wish I could give this talk retroactively from a month from now. It's going to be really cool in about a month. I've tried to tell you things without telling you things about things you might want to pay attention to. The star formation rate is history of time, extreme systems that are more unlike what we've seen before, being able to probe alignment and misalignment. Those are things that have been holy grails for the field for the last decade, and now they're starting to come into reach. GR is hard. One of the things that I personally am doing right now, I will tell you, and one of the reasons we don't have a paper out yet is GR is hard. If you may remember way back, let me zoom back here, where we presented an analysis of what we thought a pair of black holes was. And you'll notice there are two sets of curves on this plot. Why are there two sets of curves? Because GR is hard, and this is one group's approximation, and this is another group's approximation, and they are not the same. And some of those approximations are going to be more or less different. And the more interesting the source is, sometimes the more different those answers can be. So that's unfortunate. And so we're working on that now very hard. We have a lot of people at RIT who work a lot on these detailed numerical simulations. And so we're trying to address that and understand how that affects things. But future is bright. We're already in the 50 mergers in a year sort of regime now. Next few years, it will start to get pretty painful. We're working now at prototyping the next generation of instruments. Just on the ground, you'll get hundreds of thousands of neutron stars a year, so it's pretty frightening, but also fantastic. And that doesn't even talk about all the fantastic stuff that's going on with space-based interferometers like LISA, which will measure a different type of source to ridiculously exquisite precision, literally mapping out the space-time of a emerging black hole. So it's a really exciting time to be working in this field, and hopefully I've tried to convey some of that excitement to you. But let me pause now for questions. Where is the chat window? Questions.
So, questions for Richard? Maybe a couple people typing.
Richard.
So once we get the yes.
Am I coming through? Yes, I am.
Yes.
So I know that I understand a little bit about degeneracy, electron degeneracy in connection with, say, white dwarfs. And I think you're speaking of quadrupole degeneracy. I'm not sure exactly what that is. Can you say a little bit about that?
Okay, now I'm in. So the gravitational wave signal, I'm trying to find where I have the best diagram of this. The gravitational wave signal is very, well, this is the diagram I have. So the gravitational wave signal is dominated by, at leading order, the quadrupole radiation. So it's dominated by the electromagnetic radiation is dominated by a dipole moment. Because of symmetry, there's no monopole moment because it's a spin 1 vector field. A gravitational wave is a spin 2 field, and so the dipole contribution is 0, and so the leading order term is a quadrupole term, and so therefore you need a quadrupole mass motion, which I will corresponds. In fact, it's very similar to the nature of the wave motion that you get as the object is moving along. You see this kind of stretching and squeezing pattern. This sort of stretching and squeezing pattern will produce a quadrupolar distortion that can also source gravitational waves. Now you can have higher order multipoles, just like with the monopole and dipole, quadrupole. You can just keep going up in multipolar order, and the natural pattern of the wave will get more complicated. So that's one type of degeneracy that's being broken. In that it's not the quantum mechanical degeneracy; it's just the where you mean degeneracy in a quantum state. This is more a it breaks the degeneracy of the angular pattern, in that the angular pattern is not dominated by one multipole component in one angular pattern and one frequency. There's actually multiple frequencies. Let me get this other diagram up. There we go. So there's multiple tracks in this time frequency plane that are contributing power. So there's one track here, and then there's another track here that's contributing. So there's the off source. Did that answer your question, or was I answering a different question?
It may be, but the other way that degeneracy is used is interfering with my thinking a little bit. So multiple but finite number, and are there sort of preferred states that could be in?
Oh, I did that backwards. So the dominant. So it's kind of a hierarchy for the purposes that we're interested in. There's basically they occur at multiples of the orbital frequency. So there's the orbital frequency. There is little radiation at the orbital frequency. Most radiation comes out at twice the orbital frequency. And then for every integer multiple of the orbital frequency, there's power that goes out at that frequency. Depending on the number m that multiplies the orbital frequency, you're going to get different types of angular distribution of your power. And so your radiation will come out in different amounts in different directions. And so let me
About the
go ahead.
So that'll tell you something about the dynamics and the geometry of the event then.
Yeah, and so basically every I apologize, I'm going to use the math. So each one of these functions basically for every m is going to have a different natural frequency, and they're going to have different angular patterns. So that usually there's basically two terms are in the sum. There's the 2 and 2 minus 2 terms only are the two dominant terms. For a more complicated system that would, if it's asymmetric, you also have the 2-1, the 3-3 terms are also going to be significant. And they'll occur at different frequencies at, for example, 1 times the orbital frequency or 3 times the orbital frequency, and they'll have a different angular pattern. The key thing about this different angular pattern is they're more significant in some orientations than others. And so their presence, if you can identify them in the signal, lets you pin down that orientation better. And also because it's a signal at a different frequency, you may be, for example, at higher frequencies, the detector is more sensitive at higher frequencies. And it's also telling you about a different part of the signal. So it allows you to basically break some degeneracies in the, because you basically have, think about it like you have a radio that's transmitting the same station through two different noisy frequencies over the on the radio, and you have a pretty lousy signal. But by combining the signals that you receive about that same radio station together along these two noisy channels, you get more information than you would if you had just one or the other. So it's a separate communication channel that's supposed to encode all the same information. It's just encoding it in a slightly different way. And so by having this second channel available, it allows you to combine. It allows you to you can use it to get more information out than you would if you just had the one radio frequency.
Thank you.
Dave Bishop had a question on explaining what the LISA probe is.
All right. So the LISA probe, I'll go back to my non-functioning demonstration. So imagine that you have, instead of an interferometer like this, imagine you had an interferometer that are 3 spacecraft. And what they're going to do is they're going to bounce light back and forth between the 3 arms of the spacecraft. So it's not just 2 arms, it's 3 arms. And now these are going to be spacecraft that are going to be flying in space and rotating around, rotating. So this entire constellation is rotating and following the Earth. So this is a large distributed satellite system. So that's what LISA is. It's basically, it's like LIGO in space. Now, the nice thing about LIGO in space is the natural frequency that you're sensitive to is basically related to the light crossing time. And so the light crossing time, because we're storing it in the arms, we're naturally sensitive to a few hundred hertz. But if you make the detector a lot bigger, you can be sensitive to much lower frequencies. And so by taking it and putting it in space, and basically making the distances so much larger than what you can achieve on Earth, because the Earth, you can't dig a hole through the center, and even then, LISA is much bigger than the Earth. Because you make the detector so big, you can be sensitive to much lower frequencies that you could never detect on the Earth. And you can go after sources that produce those very low frequencies. And so low frequency means, if you think about it, longer orbits from, basically more massive systems, for example. So this allows you to go and look at the orbits, not of just the sort of black holes that you get when stars blow up, but these LISA is big enough that you could begin to start to see the gravitational waves from some, small supermassive black holes that are about 1 million times the mass of our sun. It's the sort of thing that LISA can begin to be sensitive to. It's usually a little bit less than that, like 10 to the 4 would be a little bit better. So that LISA can be exquisitely sensitive to these supermassive black holes. And it can also detect the same thing that LIGO detects, in fact, just a lot earlier in time. And it can also detect very asymmetric mergers, like 1,000 to 1 is one of the preferred sources for LISA that would last for a really long time. But loosely speaking, LISA is a much bigger detector that's sensitive to much lower frequencies because it's much bigger. David, did that answer your question, or would you like more?
Yep, that sounds good. Gary asks, what percentage of the increasing number of events in O3 do you expect to be real gravitational wave events versus something else?
Why do you think we didn't find more when we went back and looked? So there are some that are not real, that are retracted. And so we usually tell, if there's something that was made public, we usually get rid of it pretty quickly if we think it's not real. However, if we find something new, we don't necessarily go out and immediately say, hey, we found something new after looking more carefully. And we're pretty clever people, people who work on these things. And so the number may be larger when it comes out than the numbers you see here, by a factor that is not ridiculous, but you should expect a larger number of real things. There are a couple oddballs always, and it's like, what the hell is that? We just had an email chain today about one that's really been annoying us for a long time. But yeah, there's gonna be more. I honestly, I could tell you how many are going to be in O3A, but I'd have to kill you. But it is a significant number. So right here, the difference between, so there's 10 to, what is that, 50? So this sort of says that we have about 40-ish coming in O3A. So I mean, that's the right order of magnitude. It's not going to be that far off. But definitely, you should expect to see things that were not previously available. So pretty high. Does that help?
That's cool. Yeah.
Okay. Can we make coffee? No. We drink coffee. We can't make it. Time scale for the event. Okay, let me read that. Black holes. This is a long one. Merging. Timescales. Okay, so GR is a dimensionless theory, which is in many ways is nice. If you have a model for 2 supermassive black holes merging, you can use exactly the same equations to describe the merger of two 1-gram black holes. Same equations work. The problem is that the time scale is proportional to the mass. It's a dimensionless theory, so everything scales with the mass. The mass is the only scale in the theory. And so if you have a supermassive black hole that's 10 to the 6 solar masses, so your natural time scale will be 10 to the 6 times longer than the time scale for a merging black hole, starting from the same initial conditions scaled down. So we're usually interested in the last few tens to hundreds of orbits. And for us, that will last anywhere from, let me go back to that video again at the beginning, where maybe if I paste, this will still work. This can still work. Okay. Try this again. So you'll see the last few can be milliseconds, but the entire orbit will typically be seconds. For a binary neutron star, it was quite a bit longer, but most of the time scales for the orbits that we're interested in are a few seconds or less. If you make it larger, the larger it gets. The starting, if you start it from the same scaled position, obviously that scaled position gets larger, but it also goes to a lower frequency because frequency goes as 1 over time. So it depends on what you consider your starting point. If you're starting at the same frequency, if you make your black holes bigger, but you want to also start at, let's say, 20 hertz, then your in-spiral time actually gets shorter, not longer. Now, that seems paradoxical, but it's true. If you take two black holes and you make them bigger, and you start at the same frequency, you're effectively starting in an orbit that's farther in that in-spiral process, and therefore your in-spiral time it can be quite short. So for very massive black holes, the in-spiral time is extremely short. So you'll typically only get 1 or 2 cycles at 30 hertz or so. For something that was 200 or 300 solar masses. Binary neutron star mergers are much longer, and so you can actually, they're so long that we are now prototyping an early warning system. This will be public, where we will say in about 30 seconds there's going to be a black hole in this direction. Go look. And so that will that's being prototyped right now. And so for 04, the plan is we will tell you before they happen where to go look for a binary neutron star merger, which is cool. It's very cool. And hopefully people will enjoy it because we have our latency is going to get a lot lower. Like it'll be negative latency. We'll tell you where to look before you go look. Okay. That was Tony. You're able to take gravitational wave mergers and very discovered expressions. So measurable is an important thing to. So I can't hear ultrasound or I can't hear infrasound. So and also so they're measurable. We have an instrument that's sensitive to certain things. Other instruments can be sensitive to other things. For example, you can turn a galaxy into a gravitational wave detector by doing absolutely nothing at all. A galaxy is full of pulsars. The pulsars provide a timing signal, and by timing those pulsars, your galaxy is a gravitational wave detector. So that was sensitive to very low frequencies. It is in principle sensitive to frequencies of order the light crossing time of the galaxy, but that's kind of crazy. More realistically, you would use it to probe longer frequency signals like with years to tens of years, because most people don't have multi-civilization year-long postdocs who can do their data analysis for them. So, for example, the motion of stars in the galaxy, the natural time scale of that is very low. And so you would need an instrument that can that probe those signals. So, for example, if you would need to have an instrument that could probe those signals and disambiguate them from any other environmental effects, keeping in mind that gravitational wave effects are very small and subdominant to a lot of other things in most cases. What you need to detect gravitational wave effects is have them be some unique feature, like in the cosmic microwave background. There are B-mode polarizations that are very difficult to produce. And what you try to do is look for those. The problem is they can also be produced by other things, like famously gravitational lensing. So disentangling the primordial contribution of gravitational waves even in something as pure as the CMB, where they were a relatively strong and distinctive feature, it's hard. So it's really a question of instrumental design. It's not that the gravitational waves aren't there. All of you are making gravitational waves right now. The problem is really that finding an instrument that's sensitive enough to detect the gravitational waves you emit, that observable part is the hard part.
So I think you were saying that there's, for two, let's say, potentially merging objects, that there can be a kick of gravitational waves from each one that makes it tree in order for
We lost you, Jeff.
then that's massive influence such an event.
I lost a good chunk of that sentence, but I think the question was about recoil kicks and how they can have an effect.
Yeah, so you mentioned the recoil kicks, and I believe what you were saying is that in order for objects to merge, that they had to have the right spin orientation and such. And so one question is, am I reading that correctly? Or if not, how do you explain it? And then can a third object influence the
Yes and yes. In fact, you read that. I didn't even say it very carefully, but you completely interpreted that correctly. If black holes have no spin, the kicks are pretty small, and so it's possible that you have no spin, that the kicks will be small enough that the black holes will be retained. If the spins are bigger and they have the right, then the kicks are a little bit larger. But the kicks get really big, and this is something that the RT groups have worked very hard on. If the spins are large and misaligned a little bit from the being spin up, then the kicks get extremely large, to be 2,000 kilometers a second. Our globular cluster's binding potential is 20 kilometers a second, so more than enough to eject from anything that you could possibly be inside. And so you're completely correct. If the spins are actually large and not have magical special orientations, like they're not aligned, then you'll typically be ejected. And so the only way that you can have a globular cluster scenario work is you need to have very low spin, or you need to have alignment, which is impossible for a globular cluster. So globular cluster scenarios basically only work in models where spins are zero. And that's one of the reasons why I wanted to highlight the spin on 04, this one right here. We have a black hole, and the more massive one is spinning. If that's true, that thing right here had better not be merging. Basically, could not have. If that's merging with things, it's going to be producing recoil kicks and ejecting it from stuff. And it can't be something where the remnant product of its merger is going to be sitting around and being used for another merger in another generation. So black holes of that spin tend to be very easily ejected from globular cluster environments if they're merging with another comparable mass black hole, and therefore you tend not to build up in this hierarchical scenario. You would not have this process here because you'd have this process, but then this thing would get transported away, and you wouldn't have the next generation occur. So you'd form one generation of black holes, but that generation would be immediately removed, and you would never be able to make even bigger black holes from their descendants. And so that was what I was trying to imply with that. Okay.
Okay, thank you.
Any other questions? Well, Richard, thank you so much. It sounds like we got you about a month or two too early.
Yeah. I would show you my other screen, but I'd have to kill you. It's going to be fun. Hopefully you'll You'll appreciate the early hints, the breadcrumbs that I've tried to leave. It'll be I think some things will be pretty clear what I was trying to say. So enjoy.
Appreciate it.
Thank you so much.
Appreciate it. All right. With that, I would encourage you. David asked if we could push their server a little farther. If you want to put your webcam on and chat for a little bit, why don't you join us? We can have a little talk together if you guys are interested. So put on your cam. We'll push David's server a little bit. See how much of us they can stand. So if you're not on and you want to chat a little bit, go ahead. I'm going to take the presentation down so that we can get rid of the presentation. Let me see. How can I do that? There we go. There we go. Let's that's not what I wanted to do. You guys not see the presentation now? It's over on the side.
No, it's still there.
All right, I just did it for myself. Let me see if I can.
Yeah, each person can minimize it, and then it gets rid of it.
Oh,
So
okay.
the cameras pop
Yeah.
up.
Yeah, so if you push the little minus sign up in the upper right of the presentation, all the video cameras get enlarged, and you can see everybody a little more clearly. If anybody else wants to join up, good to see you, Mike. Does anybody had a chance planning on doing any observing soon? Anybody buy a new telescope so it's going to get cloudy? Usually that's the curse.
So it's supposed to arrive today, and I don't know if you hear. My telescope is supposed to arrive. I had a new 127 millimeter refractor is supposed to arrive today, and it was coming in 2 boxes. And it looked like the one box was going to come today, and another box was stuck in transit. The box that was supposed to come today was the heavier of the 2 boxes, it said. And of course, it arrived, and it was the finder scope.
Yes.
So that's why it's clear out today, not cloudy, where I am.
That's funny. That's funny. So who's going to get up early in the morning to try to catch Comet Swan? It is kind of faint at 5 points, whatever. It's gonna be another week or two, but it's still kind of faint at 5.8 or 6. You're gonna need to really look for it. But the chart's pretty good. It's gonna be in not Pegasus, Perseus. So should be fairly easy to spot, even with a pair of binoculars. Nobody else wants to put their webcam on. Sorry, Dave.
Tonight.
See, Galileo joined us. You look on the people on the left.
Who is that?
I don't know.
He's old.
He's old. Yes. It's an honor to
He's
have him
got a
here.
really, really inferior scope.
There's a little 2-inch scope. Yeah. So it doesn't sound like we're gonna have any MEs this year. That's all canceled, right, Carol?
Any me's right now there's nothing, I just can't think of any way other than remote perhaps observing, but we're not actively pursuing that right now. It's the first year in 20 years that I've been associated that we couldn't do it. It's breaking my heart.
No kidding. No kidding.
And
Yeah.
Joe just said he had to cancel all the scout events, right?
Yeah, Joe sent a note out that because school was canceled, or New York State has canceled the rest of the academic school year. All his school year events that were going to be planned at the Ferris Center are canceled now too. So we're still going to hold out hope we have our Rochester Fest. So we'll be doing some more of that planning this week, this coming week. But Who knows? Who knows what we're going to be able to do? You know, maybe we'll all be wearing masks when we're seeing each other. I don't know. We don't know what we're going to be doing. It'll be interesting to see what happens. Let me see. I'm missing some of the chat because I got this all open here. Bob Easterly says he's going to give it a shot. That's the Swan. Good. With social distancing from the Razor, I bet there's a lot of Galileo lookalikes in the club. That's good. Thanks, Bill. I know we're going to find out what everybody's natural hair color is. I know I could see a barber soon. My hair's growing out pretty long. Has anybody taken advantage of going to the Ferris Center and on any other observing out on the lawn or anything? We've had some nice nights. Nope.
Yeah, there was one night last week I grabbed my scope and I was tired from watching the kids. So I just pointed at the moon and looked at that for a couple, like 30 minutes or so, and then went back inside.
There's a lot to see on the moon.
It really is.
Actually, after watching that video from last Thursday, I almost want to look at some of the stuff that he was showing us there. It's pretty amazing.
Did anybody try the Lunar Trek, that Trek application from NASA? For both Trek and also Mars? That was really interesting.
I haven't tried the Mars Trek. I tried the Moon Trek, but I gotta work with it a little bit. It's a little tricky to use.
If you, instead of looking at the flat plate, if you change it to 3D where you see the globe, you can spin the globe around, you can zoom in, zoom around it, and you can do the same thing with Mars. You can scoop across the surface of the planet in detail.
We're going to give Steve Fentress a run for his money.
There we go.
Over at the planetarium. You could do that with the Digistar software that's there, but this is it's pretty powerful stuff. All right, well, I'm going to stop the recording at this point.
But why is a lot of the videos everybody's really